Hello again, everybody. Today we're going to be doing section 5.6, which is where we learn about phase shifts and sinusoidal curve fitting. So let's jump right into it. Let me pull up the slides. There we go. And let's take a look at the overview to get started. All right, so the first thing we're going to do is we're going to talk about graphs of this form, f of omega x minus phi, just to take a look at the general theory of what happens with these phase shifts. Then we'll look at graphs specifically of this form, basically putting all of the different transformations of our sinusoidal curves together in one. We'll do another example with cosine instead, and then we'll finish up with sinusoidal curve fitting. Curve fitting is basically, it's kind of like going in the opposite direction. If you have a set of data, can you construct a sinusoidal curve that agrees with that data to some degree of accuracy? So that's what we'll do there. But let's talk about these first. So if you remember from section 1.5, if you subtract a value phi from the input of a function before you evaluate it, that results in a horizontal shift, left or right, depending on the sign of phi. By the way, this little symbol here, this is the Greek letter phi, and it's spelled Phi, phi. There you go. Yeah, and then this one is omega, just as a reminder. Oops. Omega. There we go. So remember also from section 1.5, if you multiply the input by some scalar omega, then what that does is it results in a horizontal compression or a stretching, right? Depending on the size of omega. And then if you do both of these things, if you have this factor omega, and then if you have this shift phi right here, or that value phi, then both transformations will occur. You're going to get a horizontal compression or a stretch, and you'll get a horizontal shifting, left or right. Okay. So for now, just to look at how this is going to work, we're going to suppose that omega is positive just for convenience. This theory, everything we're about to talk about, works no matter what the sign of omega is. But for now, let's just say that it's positive so we can avoid having to deal with double and triple negatives and those kinds of situations. So remember that something that looks like this, that is going to be a shift of the graph of f of x horizontally by phi units. Now, if you have a function that looks like this, f of omega x minus phi, then that's a shift of the graph of f of x horizontally by phi over omega units. Phi over omega units. So there's a bit of a subtlety here. The reason that that scalar omega is affecting the shift itself is because that value phi, that shift value, is being applied to the variable omega x, not just x, right? So if you look up here, this value phi, it's being subtracted away from the amount omega x, not just x. So because of that, omega affects the amount of the horizontal shift. So this I feel like is a little bit more intuitive here, the very last line. If you shift omega x by phi units, that's the same thing as shifting x by phi over omega units. So there you go. So ponder that for a bit, but that's essentially how it works. And let's look at it. Let's look at how it applies to a specific sinusoidal function. Here we go. So now we're looking at graphs of this form right here. And now we have all of the different possible transformations of our sine curve, of our sine function. Remember what these little pieces do. A affects the amplitude, and it also affects if the graph is going to be reflected vertically. Omega affects the horizontal compression or stretch. For this particular function, for the sine function, it affects the period. Phi is what we just learned about. Phi is going to give us a horizontal shift. And then B is a vertical shift of the entire curve up or down, depending on the value of B. So what's nice is that if you factor out omega x, I'm sorry, if you factor out omega from omega x, it results in this form on the right here. And while this form might look a little complicated on the surface, it's actually a pretty nice form because it basically pulls apart all of the things that are going to affect the graph of the sine curve. So we can see everything that's going to be affected using this form right here. Now, one thing is when we graph this curve by hand, that phase shift, phi over omega, the phase shift is going to affect the key points. So if you recall from the previous sections, when we were graphing sine and cosine by hand, we had to find these key points. The way that we did it was we took the period and we divided it by 4, and then we basically just counted 1, 2, 3, 4 of those values. So now that we have this factor omega that's influencing things, it's also going to influence the key points. And we're going to see exactly how in just a minute. Yeah, and I have this note here, the very last line. More specifically, one period of this function that we're going to graph, it'll begin at x equals phi divided by omega. And so the short story is that our key points are all going to be shifted by this amount. So the key point process that you learned before is still the same, but now you need to shift all of those things by whatever the phase shift is. So let's look at this. We had a similar proposition in a previous section, but if we have a general sinusoidal function of this form or this form, then the amplitude is the size of A, the period is 2 pi over omega, because the period of sine and cosine is 2 pi. The phase shift is phi over omega, and I forgot to put it here, but the midline is going to be at y equals b. So then when we're graphing, the key points are all going to be right here. So the first one is going to be at phi over omega plus 0 p times 4, right? That's just what I said over here. So the first point will begin at phi over omega, because 0 times anything is 0. Then the next key point will be at phi over omega plus 1 p over 4, and then it'll be plus 2 p over 4, plus 3 p over 4, and plus 4 p over 4. And that's pretty much it. That's how you find all those key points, right? So let's try an example. Let's take a look at this one for a minute. What we're going to do is we're going to find the amplitude, the period, the phase shift, and the midline of the following function, and then we're going to graph the function precisely. So what I want you to do first is just take a minute and think about what the question is asking, and think about what you think you would need to do first. Okay, now just take a moment and say something out loud to yourself. Remember, the speaking portion here isn't that you need to say anything to anybody in particular, it's just to give your brain that feedback. So just say something out loud to yourself, maybe about how you would start the problem. All right, now try to work it out yourself. See if you can find the period, the amplitude, the period, the phase shift, and the midline, and then we'll do it together in just a moment. Okay, let's try to do it ourselves. One thing I noticed right away is that the amplitude is going to be 3. We can pick that right out. And the midline is going to be 1. So I have that right here on the slides. Right away, we know the amplitude is 3. The midline is going to be 1. Now, notice here that the value omega for this function is 2. So omega is equal to 2. So if we want to know what the period of this function is, it's going to be 2 pi divided by omega, which is going to give us pi. 2 pi over 2 is just pi. Now, what is the phase shift? The phase shift is phi divided by omega, and this number right here, this is the number phi. In this case, it's pi. So if we want to know what the phase shift is, it's going to be pi divided by 2, and that's what we have right here. Okay, so now we have all the info we need: amplitude, period, phase shift, and midline. Now we just have to find the key points. So how do we find the key points? We're going to take the period and divide it by 4. The period we just found was pi, so we're going to take pi and divide it by 4. And then our key points are just going to be our phase shift plus 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4. Just like right down here. There you go. And like I mentioned in the previous lecture, if you want to simplify those results, you can. I don't require you to, and I honestly feel that it's often more revealing and more clear when they're not simplified, because then you can really, really see what's going on. You can see what the phase shift is, you can see where all the key points are and how they're being generated. But if you do want to simplify them, it is not wrong to do so, and you're very welcome to do so if you think it looks nicer or if you ever need to. But don't feel like you have to. That's all I'm saying. Okay. Now, with all of this information, hopefully the graph that you got looks something like this. So this is what I got when I graphed it. Let's point out all the little details just so that we can see that we're on the same page. The first thing I want to point out is the phase shift. So notice that the graph, the first period of this graph is starting at pi over 2. And that was exactly what we were saying just a few moments ago, right? The graph will begin at that value, pi over 2. The other thing I want to notice is that from here to here is one period of the curve. And if you look at the end value and the starting value, in this case I simplified them, you'll do the difference. Take the end value and the starting value, subtract them, and then see if you actually do get the period you calculated. So here we would have 3 pi over 2 minus pi over 2. Well, that's 1.5 pi's minus half a pi. So if you got 1.5 and you take away half, you've got 1. So the period is pi. Just as we calculated, right? So everything is good there. Next thing to point out is the midline. The midline is clear on the graph. It's at the point, or I'm sorry, it's at the line y equals 1 right here. And that's the midline. And then also we can see that the amplitude is 3, as we predicted. This distance is 3. And our key points are exactly where we suspected. So pi over 2, and then pi over 2 plus 1 pi 1 1 pi over 4, and then plus 2 pi over 4 plus 3 pi over 4 plus 4 pi over 4. And there's all of our key points. All right. Okay, let's do another example. So here's another one, and we're going to do the same thing as before. So think about it for a minute. Take a look at the question and just ponder what you would have to do first and how you would go about it yourself. All right, now say something out loud to yourself about what you're going to do with this process. Where are you going to start? What was something from the last process that you thought was the most difficult? Just say anything out loud to give your brain that feedback. All right, now try to work it out on your own. See if you can find the amplitude, the period, the phase shift, the midline, and graph the function on your own, and we'll do it together in just a moment. All right, let's do it together. Couple of things that I noticed right away just by looking at the function itself. Oh, come back. Where'd you go? There we go. Is this. So the amplitude is going to be 2. And because that leading coefficient there, a, is a negative number, I know that this is going to be the graph of the cosine curve, but it's going to be reflected vertically, right? It's going to be reflected vertically because a is a negative number. So it's going to flip around the midline. And the midline is easy to pick out. The midline in this case is going to be y equals 1/2. So that's right in the middle. Then we see that omega is pi, and that's going to affect our key points. It's going to affect the period, etc. And then this number here is phi, but we have to be a little bit careful. We have to be a little bit careful because if you notice the structure up here in the title of the slide, this sign needs to be a negative sign. So in our case, phi is actually equal to -1, not +1. And that's because if we want this structure given here to match this structure up here, we would need phi to be -1, right? Because subtracting a negative is the same as adding, right? So let's go through the details. Like I just mentioned, we know that the amplitude is 2. We can find the period by looking at omega. In this case, omega was pi. So when we do 2 pi divided by pi, we get that our period is 2. And then phi over omega, the phase shift, is going to be -1 over pi. -1 over pi, for the reason I was saying in the previous slide. And then the midline is y equals 1/2. And then lastly, this note at the bottom is what I had mentioned earlier, because A is negative, we know this graph is going to be flipped vertically about the midline. Another side note I want to make here, don't be put off by the fact that our period doesn't have a factor of pi involved in it. It's actually very common for the period of a function not to be something like 2 pi or pi over 2 or 3 pi over 4 or anything like that. A lot of times the period will just be an integer, and a lot of times the period will be 1 because we want to scale it in that way. So sometimes when we observe oscillatory behavior in nature or just in theory, we want the period to be something unital, something where we can say, oh, it's going to be repeated every unit. And every unit means 1. So a lot of times the period will just be 1. And you can you can change the value of omega to make the period 1. So just keep that in mind. The values for all of these can actually be any real number. It doesn't have to be something with pi in it. It doesn't have to be an integer. It doesn't have to be a fraction. It could literally be any real number that you want. And honestly, in reality, when you're actually doing research with these types of functions and these types of curves, those numbers, a, b, omega, and phi, can be very, very nasty numbers, maybe crazy irrational numbers. They can be all sorts of things. So don't let that get to you. Just keep in mind that they're real numbers and they could be anything, any real number. All right, so now the next step is we're going to divide the period by 4. Remember, the period in this case is 2. So p over 4 is 1/2. P over 4 is 1/2. Now, our key points are going to be the phase shift plus 0, 1, 2, 3, 4 of these values 1/2. So here's the first key point. Here's the second one. It's the phase shift plus 1 1/2. The next one is the phase shift plus 2 halves, and then plus 3 halves, and then plus 4 halves, and so on and so on. All right. So we've got everything we need. We know the amplitude, we know the period, we know the phase shift, we know the midline, we know all the key points, we know that it's a cosine graph, we know it's going to be reflected vertically. So with all of that information, hopefully your graph looks a little bit like this. Here we go. All right, so just like before, let's go through all the details and just verify what we're looking at. First thing is, notice the phase shift of -1/pi. So the whole graph got pulled backward. The whole graph got pulled to the left by -1/pi units. Or I should say by 1/pi units, right? Pulled to the left by that much. So that's because our phase shift was a negative value, so it got pulled this way. All right, now let's look at the period itself. So one period of the curve is right here, okay? And if we look at the final value on this of the period, and we look at the initial value where the period starts, and we take the difference, we can see that the difference is going to be 2, which is exactly what we expected the period to be, right? So we calculated that the period was 2, and there we go. It is actually 2. Right, next thing, the midline is 1/2, as we figured, just like so. Notice also that this is actually the graph of cosine, but flipped vertically across the midline. So cosine, remember, cosine normally looks like this, right? Starts at 1 and goes down and then goes back up to 1. But now because a was a negative value, the whole thing is flipped vertically, right? And then lastly, here's all of our key points. These ones I didn't simplify like I did on the last example. So a key point here is -1/pi, and then it's going to be, where is it? Right here, -1/pi plus 1/2, -1/pi plus 2 halves, which is 1, -1/pi plus 3 halves, -1/pi, I should have put this one over here, there we go, -1/pi plus 2. All right. And that's the whole deal. So now you have all of the skills, you have all the tools you need to graph any general sinusoidal curve whatsoever. You've got all that you need. So now on that note, let's go in the opposite direction and let's talk about sinusoidal curve fitting. So many phenomena in nature in nature and not nature exhibit oscillatory behavior, or in other words, periodicity. And one of the things that I always like to tell my students is you don't need these ideas to be rooted in reality. You don't need them to be rooted in just the observable universe, for example. We're just talking about the general idea of oscillation, the general idea of periodicity. And if you want to describe those things, you can use sine curves to do so. So there's lots of things that you've probably imagined in your head where you're like, oh, it's bouncing around or there's oscillation going on. You can describe that precisely with sinusoidal curves. So let's say you have a bunch of data that appears to be sinusoidal in nature or appears to be oscillating in some way. The question is, can you construct a sinusoidal curve that fits the data well? Can you find a quote unquote sine curve of best fit, right? Sine curve of best fit. Can we construct such a thing? Um, so if we suspect the data behaves like a sine curve, what is the actual function going to look like? And this is what's known as sinusoidal curve fitting, going from data to an actual function that models that data to some degree of accuracy. Okay, so how do we do it? If we want to find such a curve that fits our data to some degree of accuracy, we need to construct this function. We'll use sine for our model because remember, cosine is just a shift of sine. So we can just use sine and everything will be fine. So if we want to construct this function, we need to find good values for a, b, omega, and phi. That's what we're looking for. So how do we find the good values for those numbers? That's what we're about to figure out. So to determine the value of a, what you do is you take the largest data value and subtract the smallest data value and divide by 2. All right? So why does that always work? You should always be asking such questions like, why is that a good way to construct A? Where did you come up with that? Why does that make sense? Well, remember that A is the amplitude of the curve, right? So there's a midline, and the largest maximum, or see, I should say the maximum of the curve will be A units up from the midline, and the minimum will be A units below the midline. So if we find the largest data value in our set and the smallest data value in our set, find the distance between them, and then cut it in half, that'll tell us what the amplitude is going to be, or the signed amplitude, you could say. So it doesn't matter which one comes first. You can just take the largest minus the smallest and then see what value you get, and that'll basically give you the number that you need to use for A. Okay. Now, how do you find B? So B tells you what the midline is. So maybe not surprisingly, if you want to find out a value for B, you take the largest data value, add it to the smallest data value, and then divide by 2. Because what you're doing is you're just taking the average of those two numbers. So again, you've got like the largest data value, the smallest data value, you add them together, and then divide by 2. And that will give you a good guess for what the midline should be. A good guess for what the midline should be. Right. Now, to determine omega, we need to know the period of the data. We need to know the period p of the data. And once we know what the period of the data is, we can use this relationship between the period of our data and the period of the sine function and how it relates to omega to figure out what omega is. More specifically, you're going to get this. So omega is basically the period of the sine function divided by the period of the data that you've got. And if you think about that for a few minutes, that makes a lot of sense, right? Because omega is some scalar that changes the period of the function, the model. And what we're saying is scale the period of the sine function by the period of our data, and then that'll be the factor omega that you need. All right. One thing I'll say is this last note here. Generally speaking, the period is usually estimated based on the data, or it's deduced exactly from the data. So one thing to think about is if your data does not seem periodic at all, then a sine curve is probably not a good curve to use to approximate it. One of the stronger characteristics of sinusoidal functions is that they're periodic, right? So generally speaking, if you're trying to approximate your data or model your data with a sine curve, there is a periodicity that you have observed, and you can figure out what the period is going to be. Maybe you can get it roughly speaking, like you can get pretty close to what you think the period is, or maybe you'll be able to tell right away what the period is. But the period is usually given or figured out based on the data. Okay, lastly, if we want to find a good value for the phase shift, that's a little bit more complicated, but here are the steps. It's not so bad once you make sense of it. But you first find the x coordinate for the first occurrence of the local maximum of the unshifted function so far. So that's the first thing you want to do, right? Makes sense on the first reading, right? No, I'm just kidding. So what we want to do is we want to find the x coordinate for where the first local maximum occurs for our model, for our function that we're constructing. And if you're using the sine function like we are, then the first local maximum will occur at this point when x is p over 4, where p is the period. And it makes sense too, because if you think about what the sine curve looks like, remember it kind of goes like this. So what we're looking for is this peak and where it occurs. So if we're using a sine function, this will occur precisely at p over 4. P over 4. There you go. If you're using cosine, then it will occur at x equals 0, because cosine starts up here and goes down like so. But for now, we're just going to use sine, right? Cosine and sine are just shifts of each other, so let's just use sine. Okay, so now that you know where the first maximum occurs of your model, then you need to find the first the x coordinate for the first occurrence of the maximum value of your data, of the data set. So where is the first local maximum of the data set? Now, once you know that, what we want is we want these x coordinates to coincide. So we're going to take their difference to be the phase shift. Their difference is going to be the phase shift. All right, so this makes sense if you think about it, because you've essentially got a bunch of data that appears to be periodic in some way. And what we want is we want the first maximum of that data to coincide with the first maximum of our sine function so that our function will properly estimate the data. And that's what you're going to do. So how do you determine the shift? You take the difference in those values, and you've got the phase shift. All right. Excuse me. That's all of it. So that's all you need to know. Let's do it on an actual example to see how it works. So here we go. Here's an example from the book, and you'll have a similar problem on the homework as well. So according to the Old Farmer's Almanac, the number of hours of sunlight in Boston on the day of the summer solstice is 15.28 hours. And the number of hours of daylight on the winter solstice is 9.07 hours. So what are we going to do? We're going to construct a sinusoidal function that fits the data. We're going to use that function to estimate the number of hours, excuse me. We're going to use that function to estimate the number of hours on April 1st, which is the 91st day of the year. Then we're going to compare our estimate from our model with the actual data collected on that day and see how they compare, just to see how accurate it is, how inaccurate it is. And then lastly, we're going to graph the function just to get a nice picture of what the graph looks like, what the behavior looks like. Real quick reminder, if you don't know this or if you haven't heard this before, the summer solstice, that's the longest day of the year. So longest day of the year literally means the day when you have the most sunlight. And the winter solstice is the shortest day of the year, and that's the day that you have the least sunset. So already, based on this information, we are looking at the maximum value of the data and the minimum value of the data. So we've got that right out. Okay, so what I want to do here is I'm going to pause for a minute. I want you to think about this question and think about how you would approach it. Okay, now just say something out loud to yourself about what you would do first, how you would approach this problem to try to construct that function. Okay, now you try to work it out on your own. Try to find the amplitude, the period, the phase shift, and the midline based on this data, and then we'll do it together in just a moment. All right, here we go. So if you remember from the instructions on the previous slides, the first things we want to find are the amplitude and the midline. So just from the data that we're given outright, we can do that. But before I jump the gun too quickly here, let's give our function a name. So I decided to call the function d of x, and this represents the amount of daylight on the xth day of the year in hours, number of hours of daylight on the xth day of the year. Now, like I had said a moment ago, the largest data value is 15.28 hours, and the smallest data value is 9.07 hours. So using those formulas for A and B, we have immediately that A is 3.105 and B is 12.175. So we know the amplitude and we know the midline is given by this line right here. Not too bad, right? Remember, the amplitude is basically take the distance between them, divide by 2. The midline is take the average of the two data values, and that's how you get those. Next, what we're going to do is we're going to find omega. So remember, omega is based on the period of the data, so we need to know what the period is before we can find omega. Now, we're modeling data that's based on a yearly cycle, so naturally the period is 1 year. But because all of our data is in terms of days and hours, we're going to convert the period to be in terms of days. So 1 year is about 365 days. So we're going to say that that's the period of our function, 365 days. Now, the period of our function is going to be 2 pi over omega. And so we can solve that for omega, and we get that omega is 2 pi over 365. And again, that makes sense, right? Because 2 pi is the period of sine, and 365 is the period of our data. So we're going to scale those together to get what omega is. Now, at this point, what we've got is this. This is what our function looks like so far. We have A, we have omega, we have B, but we don't know what phi is, and we don't know what the phase shift phi over omega is. Now we have to find that. So how do we find that? Well, we take the period and divide it by 4. In our case, the period's 365. When you divide it by 4, you'll get 91.25. And that's basically where the first local maximum of our model occurs. So currently, when x is equal to 91.25, that's where our function is going to have its first local maximum. So again, it's always good to think of the picture. Imagine the sine curve, imagine the unit circle, imagine these pictures because they just guide all of the intuition. And here what I'm saying is if sine looks like this, then this point, 91.25, that's currently where the local maximum is for our constructed model. Now, the largest data value, in other words, the maximum of the data, occurs at the summer solstice, and the summer solstice corresponds to the point x equals 172. So it's the 172nd day of the year. So what do we need to do? We need to shift the graph of d of x by this many units. So we took the difference, right? We took the difference. All right, now, because we're shifting the graph of d of x by that many units, that value is our phase shift. That's our phase shift. So this is the number phi over omega. That's the actual phase shift of the data. But now we can put everything together. We can put everything together. We already had A, B, omega. Now we've got the phase shift phi over omega. And then if you multiply everything out, that is our model, just like so. Yay, right? Yay. So this is essentially a sinusoidal curve that approximates the data based on what we were given, the number of hours in the summer solstice and the number of hours in the winter solstice, and now we have this sinusoidal curve that approximates the number of hours of daylight on any day of the year, any day of the year. So let's use it. let's use it. So if we want to know how many hours there were approximately on April 1st, we're going to plug in x equals 91 for our function. So we're going to evaluate our function at the 91st day, the 91st day. So you substitute 91 for x, and then use a calculator, and you will get that there were approximately 12.72 hours on that day of the year. So one thing I'll mention is that there's actually a lot of approximating going on. And so one thing you want to keep in mind when you're constructing models, when you're working with models, is that these are not guarantors of fact. They are approximations and estimations and models that are not precise, but they are accurate to some degree. And later on, especially when you take Calc 1 and Calc 2, just how accurate these things are becomes the interesting question, because we'll be able to figure out exactly how accurate these types of things are, and we'll be able to figure out how accurate they need to be, or I should say, you'll be able to figure out what these values of A, B, omega, and phi need to be in order for your model to be accurate to some degree. Sorry, I know that's a mouthful, but just remember that these are models, they're estimates, and so there's error involved. There's an error involved. And when you plug this into a calculator and you ask it to evaluate it, your calculator also approximates. Yeah, calculators can't even see irrational numbers. So when you plug this thing into your calculator, it's going to give you an estimate. It's going to give you an estimate to a certain number of decimal places. So that's why we use the little wavy equal sign. About 12.72 hours of daylight on that day. Now, for comparison, the Old Farmer's Almanac says that there will be 12 hours and 46 minutes of daylight on April 1st, or in other words, 12.77 hours. So our estimate is accurate to one decimal place, right? In essence, the model we constructed is exact up to one decimal place. And if you want more accuracy, then you need to change the values of A, B, omega, and phi until they become more accurate. But for now, it really depends on the context, right? How much accuracy do you really need? Right, I mean, we're just talking about hours of sunlight during the day, so maybe accuracy to one decimal place is good enough for you, or maybe it's not. But that is all up to you later on when you're doing these types of models. Okay, last but not least, we can graph what it looks like. So if you were doing this on your own, hopefully your graph looks similar to this one right here. Let's point out some of the details. For one, notice that it is a shifted sine curve. So it has been shifted, it's a sine curve. Here is the local maximum right here. So that's where we wanted things to line up. Here's the midline, 12.175. I also took the time to plot this data point. So this is essentially the data point that our model produced to give us the estimate for how many days, sorry, how many hours of sunlight there were on the 91st day of the year, April 1st. So that's what it looks like. There you go. And then that's pretty much it. That's pretty much it. So you can do this with all sorts of different kinds of data. The process is thankfully not too complicated, but one thing that can always help you is to think about the intuition, demand intuition, and think about all the little pieces that go together. Because once you can make sense of all the little pieces, putting them together is not as hard as it might seem. All right. Okay, so that's it. So let's play. You've got examples like this on the homework. You can ask questions on Canvas if you'd like, but that is it for this lesson. And the next lesson we're going to have is all about oh yeah, that's right. It's all about the inverse trig functions, inverse trig functions. So inverse sine, inverse cosine, inverse tangent, inverse cosecant, inverse secant, inverse cotangent. We'll talk about all those next time. So for now, I'll say bye, and I'll see you next time. Take care, everybody.